Yeah, hi. I'm just working with Dr. Fascetti, and I'm going to present this work now today here. Here today we are going to talk about an experimental investigation on the fracture properties of pultruded GFRP elements. For the outline of the content, I'm going to talk about the introduction and motivation, then experimental characterization and data analysis, and finally conclusion. For introduction, in the last decade, fiber-reinforced polymeric structural elements emerged as an attractive and economically viable alternative to traditional materials in the construction industry. And this is mostly due to recent advancements in the field of materials science, with the new solutions being developed for both the polymeric matrices and the embedded fibers. Pultrusion is an efficient and economically viable continuous production process that produces structural elements with uniaxial fiber bundles. Here in the right side, you can see the figures for the structure of these elements and how the fibers and epoxy get together with some process which called pultrusion to produce our different sections that we can use in civil engineering applications, and also these structures. Here, there are some examples for both building and infrastructure that engineers use this material, and nowadays they become more famous in the engineering society to use this material instead of, for example, steel. The experimental evidence shows that the transversely orthotropic behavior of the material and the relatively low strength and stiffness in the direction orthogonal to the fibers can cause a premature failure in pultruded composite structures. Here we can see two figures show some experimental study by Bank at 1994, and we can see the major problem here with the I-beam pultruded FRP elements, which is the web flange failure in web flange junction. As you see here, this is the major problem because of the lack of fiber in the these two zones showed in the in this figure. The web flange junctions can exhibit lower fiber content, as I said, as a result of the pultrusion process. This is the problem of processing in the pultrusion, and accurate predictions of the ultimate strengths of such areas are of crucial importance in the evaluation of structural behavior of structural assemblies. Here in the experimental work, the coupon sample were obtained from a pultruded GFRP structural halo section by means of a CNC machine, and three fiber directions were selected: 0, 45, and 90 degrees, the fiber load orientation degree, for the both tensile and 3-point bending. Figures shows us all our samples for tensile and bending tests. This is the figure which shows how we cut our samples from the main pultruded GFRP halo section provided for us by the CNC machine, and the figure B and C shows us the dimension. We selected both same length of 160 millimeter, and the spatial the rectangular shape for the bending, and this coupon test for the tensile coupon test shape for tensile test. For all of the samples, the thickness was 7 millimeter. The experimental test was completed, and after failure, we have this figure of the 0 degree, 45 degree, and 90 degrees. As you see, because in the 0 degree, there is 100% of fiber inclusion in the test. We have the failure in the weak fibers. Because of that, there's not such rupture in the whole specimens. But for 45 degrees, the crack path shows us the 45 degree, and for 90 degree we can see that almost there's no fiber effect and almost matrices effect here. Again, same process implemented for the 3-point bendings. Here, in the 3-point bending, we can see the 0 degree crack path line, and 45 degree and 90 degree. Again, almost same scenario happened for the 3-point bending test. If you want to see the result as the analysis, we have the stress strain behavior of all test types. The significant scatter is observed during the test, and the 90 degree orientation shows us the highest value of standard deviation and coefficient of variation. Here we can see that because of the fiber effect, we can see that the 0 degree is almost 10 times greater than the 45 degree and approximately 20 times greater than 90 degrees. Again, the stress strain behavior for the 3-point bending shows us the almost a brittle behavior in our samples, and again, significant scatter is observed during the test. And 90 degree orientation shows us the highest value of standard deviation and coefficient of variation. Here, the 0 degree shows almost 5 times greater stress than 45 degrees and almost 10 times greater than 90 degrees fiber to load orientation. And in this figure, we have the normalized stress and normalized strain data for all types of tests with different fiber, for 2 types of tests with different fiber to load orientations. And as a conclusion, the pultruded GFRP materials, we know that are novel materials that can be employed in a wide range of the structural applications. Experimental study demonstrated significant scatter in ultimate strength as a function of load to fiber orientation, and the relatively high coefficient of variation obtained experimentally suggests that the ultimate resistance of GFRP element is highly dependent on the local density and volume ratios. Finally, ongoing research will aim at quantifying the influence of local strength and stiffness on the ultimate microscopic strength by means of stochastic numerical modeling approach. Thank you for your attention, and you can contact me by this email.